Okay, so let us start. So today we have the pleasure to listen to Eugene Bronasco from Geneva on exotic B series and S series, algebraic structures and order conditions for invariant measure sampling. Please.
Thank you very much for the introduction and for this opportunity to present this project. So in this talk, I'll talk about order conditions for invariant measure sampling. And I'm going to do it in the context of, or in the framework of B series and S series. So we're going to see some trees and some arguments involving structures on trees and forests also. So let us start with a small preview. So we consider an overdamped Legendre equation of the following form. We have F, which is a gradient of a potential and is assumed to be smooth. We have W, which is a standard Wiener process, and the noise in this equation is additive. So during the study of the numerical integrators applied to this problem, we encounter grafted forests and exotic forests. So grafted forests are bicolored forests in which there are two colors, so black vertices and grafted vertices. So I'll try to show with my pointer. So the black vertices correspond to the vector field F, and the grafted vertices correspond to the noise. And therefore, and since edges correspond to a covariant derivative, the grafted vertices cannot have incoming edges. A second class of forests are exotic forests. So exotic forests are grafted forests in which all the grafted vertices are paired. So here are some examples. So these are the same forest, but now all the grafted vertices are split in pairs. So the pairing is denoted by these kind of numbers. So two grafted vertices are paired if they are associated to the same number. And here are some examples. So both kinds of forests are used to represent differential operators. And here are some examples. So on the left, we see a map F subscript HF, which assigns a differential operator to a grafted forest. And on the left, we see that the differential operator contains some noise, as Xi, which is a Gaussian mean 0 and variance 1. And on the right, we see a differential operator corresponding to an exotic forest, and it's deterministic, it has no noise. And so the relation between grafted forest and exotic forest is in the fact that the exotic forests are obtained when we take the expectation of a grafted forest, right? Since we have some noise in there, we can take expectation and we obtain exotic forests. So this relation can be better understood if we use this moment cumulant and set partition relationship where we work with Gaussians. So we have mean 0, variance 1, and all the other cumulants are 0. And so set partitions become just the pairings of grafted vertices. Yeah, but I'm not, I know very little cumulants. I was pointed out to this perspective by Kurosha Brigimifart. Okay, so this is a small preview of what we're going to work with. Now let us start with a preliminary section. So let us consider a deterministic case in dy dt equals to fy, where the problem is in Rd. So here the dimension of the problem doesn't matter, and also in general in this talk it doesn't matter. So f is a smooth vector field, and then we can take Runge-Kutta methods and use them to integrate this problem. They have the following form, and the coefficients of the Runge-Kutta methods are listed in a Boucher tableau. So what we can do now is we can take this f of big yi and Taylor expand it around y0. And then what we obtain is we obtain y1, which is equal to a certain formal sum of elementary differentials applied to y0. Right, so here we have identity applied to y0, so a vector field applied, identity vector field applied to y0, then f applied to y0, f prime f applied to n, and so on. And the coefficients in this sum are taken to be are given by the Runge-Kutta method, by the Runge-Kutta coefficients. So now what we can do is we don't have to limit ourselves to Runge-Kutta methods. We can take this formal sum of elementary differentials as an object. So we can generalize the coefficients. And this way we obtain B series. So to define B series, we first consider rooted non-planar trees, a set of rooted non-planar trees T with a single vertex tree, and then other trees follow. And then we also consider a functional over such set. Then a B series is a formal sum characterized by this functional, denoted by B of A, which is a sum of such vector fields, also called elementary differentials. And we see that the coefficients in this sum are given by the functional A applied to the corresponding rooted tree. So here we use the correspondence between elementary differentials and the rooted non-planar trees, which was studied by Cayley and in 1857. So for example, here we have F, which corresponds to a single vertex tree. Then we have F prime F, which corresponds to a tree with two vertices, and so on. So a nice property of this B series is that the exact solution is a B series. And as we mentioned before, Runge-Kutta methods are also B series. So by comparing the corresponding functionals, we can obtain we obtain the order conditions for Runge-Kutta methods. So here, for example, we have the functional A, which corresponds to the Runge-Kutta methods, and is defined as this sum over Bi. And we want it to be equal to 1, which is the value of the functional corresponding to the exact solution. And the general formula for the exact solution is given by A tau, where tau is a tree, equal to 1 over tau factorial, where factorial of a tree is a generalization of factorial of a number.
Eugene, excuse me, just a technical question. Could you remind us who are the CIs?
CIs, okay.
Yeah.
So CI is a sum over all over J of Aij.
Okay, thank you.
Yeah, I'm sorry, yeah. Thank you. Yes, so this kind of structures were originally studied by Butcher in the 60s, and then this theory was developed further by Schreier and Gerhard Wenner in the 70s, and some nice properties. So the nice property of B series is the fact that they relate in a way numerical analysis and these combinatorial structures like trees and forests. And one of such example is the fact that the composition of B series can be completely characterized or described using a Hopf algebra of Pons-Kreimer, which was introduced in '98 to handle renormalization of quantum field theory. Okay, so this is the classical theory of B series, and now let us look at S series. So in this talk, we will mostly work with S series. So if B series are based on trees, then S series are based on forests. So here we have a set of forests, including the empty forest, where a forest is basically a monomial of trees, right? So we take several trees, we concatenate them. It's commutative. And the empty forest is just the empty monomial. Then we also introduce a symmetry coefficient of trees and forests. And here we have some examples of its values. So this coefficient is denoted by sigma. And here we have a V-shaped tree. Coefficient is equal to 2 because sigma computes or counts the number of the size of automorphism group of this tree, right? So it's equal to 2 because we have an identity automorphism, and also we can just transpose the branches and we get another automorphism. The same works with this forest, right? So here in the bottom we have roots, so we can preserve the roots, and then we have identity, or we can transpose the roots and we get another automorphism. And here, okay, so we have we can permute the branches anyway, so we have 3 factorial. And now we can use this symmetry coefficients to give a formula for S series. So originally S series were introduced to study first integrals, but since we work in a stochastic context, Since we work in a stochastic context, we will work with test functions. And so we can also use the S-series concept for our own needs. So given the map phi from Rd to R, S-series are defined in the following way. We can take a B-series, which is a map from Rd to R, and we can compose it with phi. Then the result will be a certain differential operator S of A applied to phi. Right? So this S of A is called an S-series. And it can be written as a certain formal sum over the set of forests, where every term is a differential operator corresponding to the forest, which is applied to phi. And the coefficients are given by the extension of the functional A from the set of trees to the set of forests multiplicatively. And then we divide it by the symmetry coefficient sigma of the forest, sigma pi. So now, since we consider the B series in stochastic context, we will study the expectation of phi of B of A, and so it's reasonable to consider S series as a tool we're going to use. It has to be said that the approach we don't have to consider S series; it's a choice, because for example, in the paper by Adrien Laurent and Gilles Villemard, they consider aromatic exotic B series, where the root of every tree corresponds to the test function. A similar formalism is also used by Andreas Rossler, where he considered trees with the roots being the test functions. But we chose to basically remove the root from the tree, and this way we obtain a forest. And instead of studying these vector fields, we study differential operators. And also this choice also corresponds to the fact that a Grossman-Larsen of algebra can be defined either on forests or on trees with an appropriate product. So these two approaches are equivalent. Okay, so in the last slide of the preliminaries, we're going to talk about ergodic integrators and ergodic problems, or ergodicity. So in this talk, we consider ergodic integrators and apply to a certain ergodic problem. And the problem is ergodic if the average of over the trajectory can be characterized by a certain invariant measure. And since we work with an overdamped algebraic equation, we have that this invariant measure mu has the following form. So d mu of x is equal to z times e to the power minus vx dx in the end. So this v is the potential of the problem, and z is just a normalizing constant. Since we work in a stochastic context, we have multiple ways to converge to the solution. Right? We can converge in a strong way, we can converge in a weak way, and we can converge in an invariant measure if we're working in an ergodic context. Okay, so this gives us several notions of order of a numerical method. So here we have the weak order and the order with respect to invariant measure. So the weak order measures how well does a numerical integrator approximate the expectation of the solution, and the order with respect to invariant measure measures how well does the method approximate the invariant measure. So how close is the invariant measure of the method to the invariant measure of the solution. And a nice property, which was as far as I know studied in Tubaru by Talay and Tubaru in 1990. The nice property is that the order with respect to invariant measure is higher or equal to the weak order. So if you're interested in computing or approximating an invariant measure, you can actually take an integrator which has a high weak order, and it would work. However, you would be restricted a lot, because if you compare the number for the conditions for the order with respect to invariant measure and the weak order, you have much more freedom if you focus on the order with respect to invariant measure, right? So if you don't require it to be of a certain weak order. For example, there are 15 weak order conditions for order 3 and 9 order conditions for the invariant measure. So we have more freedom if we focus on the order with respect to invariant measure. Okay, so this finishes the preliminary section. So now in next 20 minutes, I guess, 25 minutes, will be split in 2 parts. In the first part, we'll talk about exotic S-series, and we will define them and also study a bit their algebraic properties. And in the second part, we will discuss a certain theoretical algorithm which generates order conditions for invariant measure sampling. And we will also prove a certain property which says that the order conditions which were defined or which were generated this way have a certain multiplicative property, which allows us to say that some order conditions are satisfied automatically. So let us start with the first part, exotic S-series. We recall that we consider overdamped Legendre equation. We recall that we will work with grafted forests, which are bicolored forests in which grafted vertices cannot have incoming edges. And we will also consider exotic forests, which are grafted forests where grafted vertices are paired. So here we have a definition of, or actually 2 definitions of S-series. So we have S-series over grafted forests and exotic S-series, which are S-series over exotic forests. We see that their definitions are almost identical, with the only exception that the sums are taken over different sets. So in the case of a series over grafted forest, we have a formal sum over grafted forests, and in the case of exotic series, we take a sum over exotic forests. Of course, we also have to extend the definition of F subscript HF, which sends grafted and exotic forests to the differential operators. And we also define a property, the sigma of pi, which are again the sizes of corresponding automorphism groups. So in the case of a grafted forest, an automorphism has to preserve the color of the vertex, right? So it has to send black vertices to black vertices and grafted to grafted. And in the case of exotic forest, an automorphism preserves the color and also preserves the pairing of grafted vertices. So also what we do is we recall that the differential operators corresponding to grafted forests are random variables, so they contain some noise. And if we take the expectation of a S-series of a grafted forest, we obtain an exotic S-series, which in itself is not a surprise, but the surprise is that the relation is so clean that we don't get any additional coefficients appearing in this relation, which is shown here. So this is due to the fact that the definitions contain this sigma coefficient. It turns out that this coefficient is exactly right to get such a nice equality. And here I have to mention that the exotic S-series is defined using a certain functional over exotic forests. So this functional on the left part of the equality, and this functional A is defined over exotic forest by taking the function the exotic forest, forgetting the pairing, and then applying A to this to the resulting grafted forest that we obtain after we forget the pairing of the exotic forest. Okay, but originally this this sigma coefficient was used to simplify the description of the composition law, and that's what we're going to do now. So now let us look at the composition law for exotic A series. We have two functionals, A and B, over exotic forests, and we consider the Konzen-Kreimer coproduct over exotic forests. So originally, the classical Konzen-Kreimer coproduct takes a forest and splits it in two parts, into a left part and a right part, by performing some admissible cuts. In this case, when we extend this Konzen-Kreimer coproduct to exotic forest, we allow the coproduct to perform with the cuts as long as it keeps the grafted vertices which are paired on the same side, right? So it cannot separate or it cannot split the grafted vertices which are paired. So that's the only limitation. Otherwise, the composition law looks the following way. So if we take two exotic A series corresponding to A and B and compose them, then we get an exotic A series A convoluted with B, where the convolution product is taken with respect to the Konzen-Kreimer coproduct. And here we see an example of how this convolution looks like. So A convoluted with B applied to some exotic tree of this shape is equal to a certain sum over all ways to split this exotic tree into two parts, into two exotic forests. And we apply A to one part, B to another part, and we multiply the results. Okay, so this is how the composition law looks like. Now let us sketch like an idea of the proof. So exotic A series can be viewed as certain maps which take functionals over exotic forests and return the formal sums of differential operators. And this map, which is denoted by ES, can be written as a certain composition of three very simple maps. So here we have delta minus 1, A sigma minus 1, and F subscript HF. So delta minus 1 takes a functional A and returns a formal sum over exotic forests where the coefficients are given by A. A sigma minus 1 takes an exotic forest and divides it by its symmetry. And then F subscript HF takes an exotic forest and returns the differential operator corresponding to it. Next, we define a Grossman-Larsen product and denoted by diamond. And we define it on exotic forests by using the fact that the map F subscript HF is injective. Right, so we say that this Grossman-Larsen product corresponds to the product of differential operators. Our original definition of Grossman-Larsen is purely combinatorial, but for the sake of this presentation, I use this definition because this is the property that we are going to use. And now, to actually prove the statement of the theorem, the composition law, we have to show that the map ES maps the convolution product onto, or yes, not onto, okay, maps convolution product to the product of differential operators. And to do that, we look at how these three simple functions transform the product. So delta minus 1 takes the convolution product and returns the product, which is the dual of the Konzen-Kreimer coproduct. So this asterisk circled is just the dual of Konzen-Kreimer coproduct. Then A sigma minus 1 takes this dual of Konzen-Kreimer and returns a Grossman-Larsen product. And then here, it's by definition, but generally speaking, it's a straightforward property that F subscript HF sends Grossman-Larsen to the product of differential operators. So the difficulty in this scheme is the middle arrow, which is drawn in red. So in a classical case, the proof of this fact relies on the fact that trees have one root. In our case, exotic trees can have multiple roots. And we have some examples here. So we have a tree with 2 roots, a tree with 3 roots, and so on. So why would they be called trees? Well, we call them trees because they are, in a way, you cannot write them as, you cannot split them further, because any way of splitting them would either cut an edge or break a pairing of grafted vertices. So in a way, they are the smallest elements in this exotic forests. So to solve this problem, we use an alternative way to prove this property by noting the following. So the Grossman-Larsen product and the product which is dual to Konzen-Kreimer coincide, they're identical on the space of uniquely decorated forest, FUD. Right, so if we add a certain decoration on the forest, then the 2 products, they coincide. Next, what we can do is we can take 2 injective homomorphism, phi and phi hat, and inject the Grossman-Larsen on the classical forest into Grossman-Larsen over the uniquely decorated forest. And then we can also do the same with the dual of Konzen-Kreimer using phi hat. Next, we can see that the phi and phi hat are related in a simple way. So phi is equal to phi hat composed of a sigma. And that's where a sigma appears. So, and these facts that are listed here are enough to prove that a sigma is actually an isomorphism. So it sends the Grossman-Larsen product to the dual of Konzen-Kreimer. And this argument is easy to extend, and we extend it to the space of exotic forests. Yes, and this finishes the first part. So in the second part, I will discuss the algorithm which generates order conditions for invariant measure sampling. And here we see some examples of the order conditions which are generated. So here we have order conditions for order 2 with respect to invariant measure. And we see that every order condition corresponds to a certain exotic forest of a nice shape. Then what we do is we prove that some order conditions can be satisfied automatically, so we can ignore them. For example, this second order condition listed here is satisfied if the first order condition is satisfied. This is due to the fact that here we have that the second order condition corresponds to a certain forest which contains the forest corresponding to the first order condition as a subforest, right? So this forest with 2 single vertices is a concatenation of the forest with a single vertex and something else. Yeah. Okay, so let us start the part. So the algorithm, the theoretical algorithm, generates order conditions for invariant measure of the following form. We have omega of pi equals to 0 for exotic forest of some nice shape, pi in EF tilde. So EF tilde is a set of exotic forest of some nice shape. And of course, if we need order P, then we take the forest up to size P. Next, we consider a renormalized concatenation product of exotic forests and denoted by square cup sigma. So in general, this square cup sigma is the dual of the D-shuffle coproduct, with the exotic trees being the primitive elements of the coproduct. And we prove the following statement. So for stochastic Runge-Gutten methods, the order condition map omega satisfies the following. So omega of the concatenation of P1, P2, or pi1, pi2, is equal to omega of pi1 times omega of pi2, which means that if we have an order condition omega of pi1 which is satisfied, which is the same as omega of pi1 being equal to 0, then we have that the omega of the concatenation is equal to 0, which means that the order condition is satisfied. And here we see an example of this property on a particular exotic forest. So here we have a nice and small exotic forests. So omega of this forest is equal to 1/2 omega of each tree in the forest. And you see that this 1/2 comes from the renormalization of the concatenation. Okay, and here are the particular values, so the explicit values of omega of the tree and then omega of the entire forest. And we see that we get rid of an ugly expression due to this property. So to prove this theorem, we're going to use labeled transformation chains. So the way that algorithm works is it takes exotic forests and performs certain transformations on them until until they reach a nice form and it can no longer do anything. So for example, we take this exotic tree as an example. It has 2 roots, which means that there is a certain pair of grafted vertices which can be moved down the tree. So it's not a very rigorous language, but what the algorithm does, it takes this pair of grafted vertices and moves it down the tree until it obtains a root which is equal to a certain grafted vertex. So it obtains a root which is a grafted vertex. Next, what the algorithm does, it takes this grafted vertex and connects it to all the other vertices. And this is how we get the first 3 terms in this linear combination. And then, in the end, it replaces the pair of grafted vertices by a single vertex, and a single black vertex. And yes, so it's a linear combination. In the end, we obtain a linear combination with coefficients -1, -1, -1, and -2. So this kind of transformation chain gives maybe a certain intuition and understanding of how the algorithm works, but doesn't really allow us to study it combinatorically, because here we have a linear combination, which is a bit unpleasant. So what we do is we split this transformation chain into 4 labeled transformation chains. And here they are. So now we have 4 transformation chains, which are labeled because it's not illustrated here, but all the vertices are labeled because in this way we can actually identify every transformation chain uniquely. So we have 4 transformation chains, in which every element is a certain graph. It's an exotic tree or an exotic forest in general, and we ignore the coefficients. So now we lose these coefficients -1 and -2 because we treat them separately. And the idea of the proof is the following. So the order condition map omega is due to the algorithm. So what happens? We take a certain series, we truncate it up to some order, and apply the algorithm on the sum of exotic forests that we have. As a result, the algorithm outputs a certain sum of over exotic forest of a nice shape. So here we have EF tilde. And the coefficients of this exotic forest are given by the map omega. So omega by tilde. And then we would like to use the LTCs, the labeled transformation chains, to analyze what the algorithm actually does. And so we write the same algorithm, but we consider the same algorithm, but now it acts over labeled exotic forests. Then we can express the original algorithm as a certain composition of 3 maps. So first map takes certain exotic forests, and labels it in a well-defined manner. For example, you can take you can have a certain order on the vertices of an exotic forest. There are such examples that come, for example, from the work of Tiglan and Filipov, where they associate some codes to trees, and then from this code you can obtain certain order of vertices in the tree. So it's just an example. So a label is a well-defined map which takes a forest and returns a labeled forest. Then we obtain the algorithm, and then we we forget about the labeling. And we prove that this algorithm over labeled forests, it respects the reshuffle coproduct. And in the end, to obtain the proof of the multiplicative property, we take the dual of this statement, the dual of the expression, and treat these forget unlabeled functions carefully, and we obtain this the statement that we wanted to obtain. So this omega of pi 1 by beta negative pi 2 is equal to omega pi 1 omega pi 2. So the main ingredients in this proof are the following. The first thing are the LTCs. So we can split, and the fact that we can split them, we can take an LTC and split it into several sub-LTCs. And we can combine them. So if we have several compatible LTCs, we can combine them into one in a well-defined manner. Then the algorithm generates all the conditions, defines a linear map. And the third ingredient is the fact that stochastic Bronasco methods form exotic S-series by extending the functional multiplicative. But it's a natural thing to do, because any B series forms an S series in this way. And so these ingredients are enough to prove the statement. And this statement is used to show that these four order conditions can be ignored. They are satisfied automatically, which means that when we apply the algorithm, we generate 13 order conditions with respect to invariant measure for order 3. And using this property, we decrease the number of order conditions from 13 to 9. And originally, this property was for order 3 was noticed in the paper by Adrien Laurent and Gilles Villemar, 2019, through manual computations. But here we generalize this property. So to conclude, in the first part, we define exotic S-series and showed a relationship between exotic S-series and a series of a grafted forest and proved the composition law. And in the second part, we introduced a theoretical algorithm that generates order conditions for invariant measure sampling and proved the multiplicative property, which allows us to reduce the number of conditions. And our ongoing work includes a description of the substitution law for exotic aromatic S-series. And yes, and I didn't say that, but all the forests considered here can also be aromatic. So we exclude aromas in the presentation just because they complicate everything a lot. But in generally, everything works with aromas too. And another project is the development of a symbolic package for manipulating the forest-like structures. I say forest-like because, strictly speaking, exotic forests or aromatic forests are not strictly forests, or aromatic trees are not strictly trees because they have cycles. So, okay, so forest-like structures. And this is done in collaboration with Jean-Luc Falcon from the computer science department. Thank you very much for your attention.
Thank you very much. Do you have some comments or remarks? No?
Well, I can ask one.
Yeah.
So there's this symmetry coefficient that is very similar to the one of Rössler. And you know, when we discuss a numerical analysis on manifolds, we introduce this kind of double edge. Do you think it's easy to extend and find the symmetry coefficient in this case? Is this just the cardinal of the set of automorphisms as usual, or something different?
So I didn't look too much into the extension to the manifolds, to be sincere. But from combinatorial point of view, if this double edge that you're talking about is non-planar, then
yeah, no, it is. I guess it is planar. Yes. Yeah. No,
planar.
it is non-planar. No, sorry. Yeah, it is
Okay.
non-planar. Yeah.
Okay. So yes, so if it's not non-planar, then the same sigma should work. Yes. So if you should be allowed to transpose the two vertices.
Okay.
Well, if they are the roots of the isomorphic trees.
Okay. Thanks.
So other questions? So if not, I may have one. Can you go back to the slide? So when you explain that you have two different order conditions, two different kind of order conditions. You know, no, it was before.
Yeah. Okay. So just froze for a second.
Yeah. Okay.
Yes.
Never mind. Yes, this one. Yes. So you have the weak order and the invariant measure order, and you say generally one is bigger than the other one. Is it always like that, or do you have some exceptions?
As far as I can say, it should be always like that.
Yeah. Okay.
It's not my main expertise, but as far as I can tell,
okay.
Yes.
Yeah. And it would be interesting to have an explanation for the gap between P and Q when this is the case.
Yeah.
Maybe I can make a comment just on this.
Yeah.
So if you look at the PDE, the deterministic PDE for the density, so it's the Fokker-Planck equation, right? And actually, approximating the invariant measure means you approximate the long time steady state for the Fokker-Planck, while the weak order would mean you approximate correctly at any short time the Fokker-Planck. So of course, if you are accurate for all time, you are accurate for a long time, but the converse is not always true, right?
Okay. Yeah.
Thank you very much.
So, other questions? So if not, we thank Eugene again.